Hello and welcome back. We were looking at problems involving the first law for a flow process. We'll continue to look at a few of them. So this problem says there's a steam turbine which has the following specifications. The height of the inlet valve from the factory floor is 5 meters. The outlet is at a distance of 2 meters. The velocities of steam at the inlet and outlet are given. Pressures at the inlet and outlet are given, and the temperature at the inlet and quality at the outlet is given, and the total power is given. We are asked to compare the relative contributions of change in potential energy, kinetic energy and enthalpy towards the work output, and also to find out the mass flow rate of the steam. So let's see how to do this. So it says we have a steam turbine. So we will draw a schematic. There's a shaft. So we have substance coming in, it's expanding, and we have it going out. So let's call these as 1 and 2. So we can also write down the first law for this process. So we have the change in energy of the control volume is whatever heat comes in minus whatever work goes out, the rates of course, because we are looking at rates, plus we have sigma of mi dot. There's only one inlet, so I'm going to just write mi dot into the energy it brings in terms of enthalpy, kinetic energy and potential energy, minus whatever is going out into the energy it takes out in terms of enthalpy, kinetic energy and potential energy. So this is what we want to find out. So we can assume this device to be at steady state, which means this is 0. In addition to this, we have mass conservation, which says that the change in mass of the control volume with respect to time is essentially rate of things coming in minus rate of things going out. If this is at steady state, this would also be 0. So mi dot is equal to mi dot, and we can say mi dot is equal to mi dot is equal to some m dot. So I can call this as m dot, and if I divide all of this by m dot, I can get small q, small w and all of these in specific terms. So that's something I can do. So I have various terms here. I have the height of the inlet valve, so that tells me the z at the inlet. I have height at the outlet, so that is z at the outlet. I have the velocity of steam at the inlet, so that is this. Velocity at the outlet, that's also there. I have pressures and temperature or quality at the inlet and outlet. So what we can do is we can use these information. There is no information given about any heat transfer. So I am going to assume that this process is adiabatic, in which case this is also 0. So writing this, I can find out w dot. So I had d by dt which is 0, I had q dot is 0. So essentially I have m dot into enthalpy plus kinetic and potential energies at the inlet minus the same at the outlet. So I'm asked to find out m dot. So that's essentially w dot divided by all of this. So the output of power is given as 10 megawatts. That's 10 power 6 watts. I don't know m dot. I need to find out enthalpies, because I don't have them yet with me. But I have kinetic energies and potential energies. At the inlet, it's 50 meters per second is the velocity. At the outlet, it's 100 meters per second. So this is 50 square by 2. This is 100 square by 2. The height at the inlet is 5 meters. At the outlet is 2 meters. So this is 9.81 into 5. It's 9.81 into 2. So I need to find out enthalpies. So let me just tabulate the information I have. At the inlet, I have 2 megapascal and 400 degrees centigrade. At the outlet, I have 15 kilopascal and 0.9 quality. So this is, sorry, I had 15 kilopascal at the outlet, not 20. So this is the information I have. I need the enthalpies at the inlet and outlet. So this working substance here, of course, is steam. So let me find out the steam tables and try to get this information. So I'm going to look at the steam tables and find out whether this is saturated or superheated or subcooled. So I have 2 megapascal and 400 degrees centigrade. So from the steam tables at 2 megapascal, I'm looking at the pressure table. At 2 megapascal, the saturation temperature is 212 degrees centigrade, and I have 400, which is greater than this. So it must be in the superheated tables. So let me go to the superheated tables, and I need a pressure of 2 megapascals, is 1.4. So here it is, 2 megapascal, and I need a temperature of 400 degrees centigrade, which is essentially this row. So what I am looking for is enthalpy, which is 3248.3 kilojoule per kg. So I have the value of the inlet. At the outlet, I know that it is saturated because I have given a quality. So it lies between the liquid and vapor lines on a TV diagram. So if I was to look at the 15 kilopascal isobar, it would go like this, and 0.9 is somewhere here. So that's essentially where the point is going to be. So I need 15 kilopascal. So I know it's saturated. So let me go back to the pressure tables for saturated liquid. So 15 kilopascal is 0.015. So that lies between these two. So what I need is HF and HFG. So HF is between 220 and 231.6. So I'm going to take the average of 220 and 231.6, which is 225.8. And I need HFG. I'm going to take the average of these two, 2375.8 and 2369, which is 2372.4. So we know that the enthalpy at the outlet is given as this. So X is given as 0.9. It gives me a value of 2360.9 kilojoule per kg. So I can put these values here now. So this is 3248 into 10 power 3. Converted into joules per kg. This is 2360.9 into 10 power 3 joule per kg. Joule per kg is also meter square per second square, which is the same as this and the same as this. So I can find out m dot, it's this divided by, this is also the same, me and mi are equal to m dot. So essentially I can also take this into one more bracket here, which will give me the value of m dot. So let me find out these values. So I get this value as about 11.3 kg per second. of steam. So that was part of the answer. I found out this part B. I am also asked to find out the relative contribution of changes in potential energy, kinetic energy and enthalpy towards the work output. So I can find out that. So I can find out the work output small w, which is W by m dot, which is essentially is this value. The contribution due to enthalpy is essentially this minus this. So the contribution as a fraction of the total work is essentially this divided by that. Which is essentially almost 100%. It's 1 point something. Then I have contribution from kinetic energy. Which is minus 3750. It is minus 4 into 10 power minus 3. And then I have change in potential energy. Which is 29.43 joule per kg. Which is 3.3 in 10 power minus 5. So what we see is that almost the entire work is essentially due to the change in enthalpy. The kinetic energy is actually increasing between the inlet and the outlet. So this actually is negatively contributing, but that contribution is anyway very small. So if this was 100%, this is like 0.4% and this is like 0.003%. So what we see is that in general, in a lot of the problems, we have usually been neglecting these delta Ke and delta P, and we see that's quite a good assumption. For example, here we see that change in enthalpy is 887 into 10 power 3, whereas change in kinetic energy is 3750. So this is 8870 into 100, this is 3750 and this is only 29. So we see that these values are much smaller than this, which is why it usually makes sense to ignore changes in potential and kinetic energy when we are dealing with substances like, say, steam and air. So the main contribution to work is only because of change in enthalpy of the substance.